Hey all. Okay. Um, so now we're getting into how light works, what light is, and how the different properties of light, wavelength, frequency, energy, speed, how that affects what we see in the universe. And then, if we can work backwards, making the observations that we can about stars, planets, galaxies, everything, and work backwards to say, well, what does that teach us about the object that's emitting the light? Right? So talking about light in general, right? All light in the universe, the the full electromagnetic spectrum, right? Like is on the second page here, right? The full electromagnetic spectrum. But at the two extremes, the radio waves are the longest wavelength and the gamma rays are the shortest wavelength. And so which of the two types of light shown has the longest wavelength? Well, yeah, radio waves do, right? Right. But what is wavelength, right? Wavelength is the length from one wave to the next, right? So if it's a greater distance from one peak to the next, that's a longer wavelength. A shorter distance from one peak to the next is a shorter wavelength. It's not more complicated than that. Which of the two types of light shown has the higher frequency? Well, remember that wavelength and frequency are go back here to this equation, right? Wavelength and frequency are inversely related. If light has a longer wavelength, then that light must have a lower frequency. What is frequency? Frequency is how many of those waves happen in a second, or how many waves happen per second. So a longer wavelength means you get fewer waves per second. A shorter wavelength means you get more of them per second. They are inversely proportional. If one goes up, the other one goes down, right? So if radio waves have the longer wavelength, then they must have the lower frequency, right? Longer wavelength, lower frequency. So then which of these two types of light has the highest frequency? Well, radio waves have to have the lowest frequency. Gamma rays have the highest frequency. And as the wavelength of light increases, what happens to the frequency? The frequency decreases. So, as the wavelength increases, what happens to the frequency, right? If the wavelength goes up, the frequency goes down. There you go. The full version of that equation on the previous page, right, is that the frequency and the wavelength are related to each other like this, where the speed of light is that some constant on the previous page, right? That's the constant that relates wavelength and frequency, is the speed of light. The energy of light, right, the energy that's contained in a single photon, a single particle of light, is related like this, where the energy of that photon is equal to Planck's constant times the frequency. So these are two of the fundamental constants of the universe, right? The speed of light is how fast light travels through empty space in our universe, and Planck's constant, h, is the constant of the universe that relates how much energy light has for a given frequency. The higher the frequency, the higher the energy. Higher frequency light contains more energy. And they are directly proportional, right? And so if you look at the full spectrum, right, the radio end of the spectrum is low energy. Why is it low energy? Because it's low frequency. Why is it low frequency? Because it's long wavelength. The longest wavelength light is the radio. And then as you go from the radio end of the spectrum through all the different kinds of light up to the gamma rays, the energy of that light is getting greater and greater and greater until you get to the gamma rays that have the highest energy light. Why do they have the highest energy light? Because they're the highest frequency light. Why are they the highest frequency light? Because they're the shortest wavelength light. All right. What type of light is reddest? In quotation marks. This is a bit of a jargon that astronomers fall into, where we say, red light, right? Remember that red light is the long wavelength end of the visible spectrum, and the blue and violet light is the shortest wavelength end of the visible spectrum. And so if we say that light is redder, we mean it's longer wavelength. Right? It's just a bit of astronomer shorthand jargon, right? Redder light meaning longer wavelength, lower energy. If we say that light is bluer, we mean it's like blue, it's shorter wavelength. So bluer light is shorter wavelength, higher frequency, higher energy. Why do we say bluest instead of violetest? Because bluest rolls off the tongue better. Even though violet light is shorter wavelength than blue light, so in our jargon, violet light is bluer than blue. Right? A little silly. So then what type of light is quote unquote reddest? Well, if light is redder when it is longer wavelength, then the reddest light will be the longest wavelength light, which is radio. And then what type of light is bluest? Well, if light is bluer when it's shorter wavelength, then the bluest light would be the shortest wavelength, which is the gamma rays. Right? So at some point, later in the semester, you'll probably find me falling into that jargon of talking about redder or bluer. And that's all I mean is longer wavelength or shorter wavelength, respectively. All right. Like I said here, and probably, good to emphasize, right? If you want, it is helpful to remember the two ends of the visible spectrum, right? The light that we can see is light between 400 and 750 nanometers. Right? These are the range of wavelengths of light that our eyes are sensitive to. Right? Everything that is longer than 750 nanometers or shorter than 400 nanometers, it's all light, it's all electromagnetic waves, and therefore it all travels at the speed of light. It's just not wavelengths that our eyes respond to, and therefore it is invisible to us. Okay. So, a little bit more looking at the relationships between wavelength and the types of light, right? What type of light has the highest energy? Well, the highest energy is going to be, right? Energy is Planck's constant times frequency. So, high energy means high frequency. H is never a variable, right? H is a constant. So, high energy means high frequency. So the highest energy light is going to be the highest frequency light. Which of these has the highest frequency? Well, look here. Blue, infrared, ultraviolet are the same. Okay, right? Highest frequency means further to the right on our spectrum here. And so here's ultraviolet, here's blue, here's infrared. So further to the right means higher frequency, higher energy. So it's got to be ultraviolet. Which one has the longest wavelength? Well, long wavelength is the left end of our spectrum here. So whichever one is further to the left would be the longer wavelength type of light, which in this case will be red. Right? What type of light has the highest frequency? Well, again, high frequency is high energy, is going to be further to the right on our diagram. So that will be green. Right? Which type of light is fastest? Aha! Trick question. I didn't catch you, did I? Right? It's all light, so it all travels at c, right? At the speed of light. 3 times 10 to the 5 kilometers per second. Or 3 times 10 to the 8 meters per second, depending on what unit is most useful. Right? So, match the types of light to their wavelengths. Okay. So these wavelengths are kind of their wavelengths sort of in the middle of that part of the spectrum. So the more important thing, rather than getting bogged down in the numbers, because on the spectrum over here, right, I didn't give you numbers, but that's fine, right? The most important thing is that these wavelengths go from smallest to largest. So we're going to list the light from longest wavelength to shortest wavelength. Nope, other way around. Shortest wavelength to longest wavelength. So what's the shortest wavelength kind of light? Gamma rays. All right. And then what's a little longer than that is the X-rays. A little longer than that is the ultraviolet. And then what's longer than ultraviolet is violet. And what's longer than that is red. And then what's longer than red? What's redder than red? Infrared. Infrared. Longer than infrared, now we're into the microwaves. And then longer than microwave is the radio wave. The radio part of the spectrum. Right? So in astronomy, right? Astronomy is not just looking at the visible light. If you're putting your eye up to a telescope, then yeah, you're seeing the universe in the visible part of the spectrum, in the part of the spectrum that your eye responds to. But now that we've built cameras and detectors that can see all these different kinds of wavelengths, all these different types of light, then you can see how bright the universe is, and you can see where the universe is bright in the ultraviolet or the X-ray or the gamma rays, right? And this part of the spectrum is, right, it's shorter wavelength, so it's higher frequency, higher energy, right? So what kinds of objects give off higher energy light? Well, hot things tend to be really good. If an object is really hot, it tends to be good at giving off higher energy light, and that means shorter wavelength. So this is why we build telescopes to look in this part of the spectrum, is because the things that pop out, the things that really stand out in this part of the spectrum are the hottest objects in the universe, right? Things like, what kind of things am I talking about? Things like white dwarfs, neutron stars, the hot glowing disks of gas that are about to fall into a black hole, supernovas, really hot things, right? So if you're looking for those kinds of super hot objects in the universe, look for the X-rays, look for the ultraviolet. These long wavelength types of light, infrared, microwave, radio wave, right? These are low energy light, right? These are long wavelength light. And so what kinds of objects give off a lot of low energy light? Cool things. What kinds of cool things am I talking about? Well, cool gas, cool nebulas, and also planets, right? Planets are not hot like stars. They're warm like planets, right? And so if you're looking for planets out there in the galaxy, look in the infrared. Because a planet like Earth is not giving off visible light, but it's warm, so it glows in the infrared. And so if you were an alien looking for the Earth, you'd be smart to be taking pictures of our solar system in the infrared. And this is the best way, this is the best way to take pictures of exoplanets orbiting around other stars. When we're looking for exoplanets, take a picture of the area around that star in the infrared, and if you see anything around that star that's glowing with a lot of infrared but not giving off any visible light, you're like, well, that's probably a pretty good sign that maybe you found a new planet. Right? So this is why we need to know the whole spectrum, is because different kinds of light are given off by different objects, different temperatures, different sizes, all of those things. So knowing what kind of light we're talking about embeds a lot of information in there. And so we'll be seeing that over the next several weeks. Well, we'll be seeing this for the whole rest of the semester. Okay? Hopefully that makes sense and you're ready to take care of the practice. So go ahead and keep on moving. Good job.